Hi, I'm Zach Chau. I'm a rising fourth year bioengineering and biochemistry student, and I am finishing up my CaNCURE co-op as a member of the Sridhar Lab. Today I'll be talking about my project, optimizing Ferumoxytol image analysis workflow. Just for some quick background, there are over 75,000 new cases of kidney cancer every year in the US. Most of these cases are diagnosed using either CT, ultrasound, or MRI. However, about 1 in 7 Americans have chronic kidney disease, or CKD, and CKD patients cannot receive CT due to its high radiation, or conventional MRI, since conventional contrast agents can be toxic to those with impaired kidney function. Ultrasound, as a side note, is oftentimes not high enough resolution to detect small kidney tumors. To solve this problem, enter Ferumoxytol. It's a safe, FDA-approved drug for iron anemia. It works with an MRI magnetic field and is cleared through the liver instead of the kidneys. It also remains in the bloodstream for longer than conventional MRI contrast agents, allowing for more imaging flexibility. Currently, the group at the Sridhar Lab is undergoing a study involving renal mass evaluation using a new type of MRI called QC MRI, used mostly only with Ferumoxytol. It provides dynamic imaging and multi-parametric maps like the ones shown below, and allows us to quantitatively assess renal mass vascularity. So that's the amount of blood vessels within a mass. This is often a key indicator in how cancerous a mass truly is. However, this study did not enroll new patients while I was working, and so my goals had to shift. And rather than focusing on analyzing patient data itself, I decided to focus on streamlining our process. So that meant eliminating barriers to scanning on different machines. So anytime we want to expand to a new machine, that would be easier to do. And it also involves streamlining our post-processing workflow via using computer programs to perform the more time-consuming tasks in our pipeline. Speaking of which, here's our current workflow. As you can see, we start with image acquisition on the scanner, and then we move to bias correction, where we correct the images for inhomogeneities in the magnetic field of the scanner. The images are then registered or aligned. Since subjects tend to move in between scans, we have to make sure the kidneys are lined up in all of our images. Then we create a segmentation, so that allows us to highlight which areas of the scans we're most interested in. So that would be like blood vessels, kidneys, possible masses on the kidneys, etc. From these segmentations, we can then create a rendering, so that allows us to get a 3D blood vessel or kidney map, which can be very helpful. And then we can also take parametric maps from the initial images and segmentations, so that allows us to get our ADC, T1, and blood volume maps. From these maps, we can then extract multiple different features, such as mean, median, kurtosis, skewness. We have over 100 features that can be extracted. And then after that, the resulting data can then be interpreted by the team. Now, what limits how quick we can gather data? Obviously, first, you've got the number of subjects that are referred. The more subjects we have, the more data we'd have. Second, we're also limited by the time it takes us to process subject data. The faster we can get through a single subject's data, the more data we have the bandwidth to process. Now, we can't control the number of subjects that are referred to us, but we can control the amount of time it takes to process each subject's data. So, in particular, we focused on cutting down on the time it takes to register our images, segment out the kidneys, and then also create ADC and T1 maps, as well as do our feature extraction. Now, this is important because it allows us to free up time for experiment planning and analysis, as well as for the scaling up the number of subjects we can handle. It also makes it easier for our work to be reproduced by other groups. And all of these streamlining was accomplished using a combination of Python, MATLAB, as well as a little bit of machine learning in the case of segmentation. Now, the key takeaways I've gotten from this co-op have been, one, it's always important to be flexible, such as, when you find out that there's not a lot of ongoing study work, how can I make myself useful? How can I fit into the bigger picture of what's trying to be accomplished here? Second was problem-solving skills. Anytime you're doing a lot of code, there's always going to be plenty of debugging to do, and so learning how to effectively solve problems as they arose was critical in my day-to-day work. And then the last thing that I really took away from this co-op is that there are many different ways to be a cancer researcher. It doesn't always have to be in a lab, like, or in a wet lab setting, like working with cells. There are many different types of research, and diagnostic research is a very key part of it. Thank you.